Every road you have ever driven on, every bridge you have ever crossed, every building you have ever walked into, there is one thing they almost all have in common. It is not steel. It is not wood. It is not glass. It is concrete. Cheap, gray, stubborn, utterly unglamorous concrete. The world produces so much of it every single year that if you poured it all into one continuous river, that river would stretch from the Arctic Circle all the way down to the frozen tip of South America. That is not a figure of speech. That is not a loose analogy designed to sound impressive. That is just the arithmetic of what we build. Concrete is the second most consumed substance on the entire planet. The only thing humans use more of is water. Let that sink in for a moment. More than oil, more than timber, more than every roll of steel and every pane of glass in every window of every building on Earth combined. After water, concrete wins by a distance that is almost impossible to comprehend. And because of that, the entire global construction industry has been designed around it. Every crane on every skyline, every blueprint in every architect's office, every building code written in every country on Earth starts from the same assumption. Concrete exists, it works, and it is not going anywhere. But here is what most people sitting in those concrete buildings have never been told. Making concrete is quietly one of the most destructive industrial processes on the planet. The cement industry alone, and cement is just one ingredient in concrete, is responsible for roughly 8% of all the greenhouse gases humanity produces every year. 8%. That is more than every commercial airplane in every sky over every continent combined. It is nearly as much as every car and every truck on every road on Earth. And unlike the emissions from a power plant or an oil refinery, a significant chunk of these emissions cannot be scrubbed away with clean energy. They are chemically locked into the process itself. You cannot wish them away. You cannot engineer around them with a better fuel source. They come from the rock. So when a team of Chinese scientists published research in 2025 that claimed to change the fundamental way concrete is made, not by swapping out ingredients, not by adding expensive chemicals, not by redesigning the material from the ground up, but by changing what happens to concrete in the few minutes after it comes out of the mixer, the global engineering community did not celebrate. A significant number of them pushed back, hard. They said the numbers were too good. They said the process was not scalable. They said the industry would never adopt it. They called it impressive laboratory science that would never survive contact with the real world. Some of them, bluntly, called it not possible. And that reaction, that wall of professional skepticism from some of the most experienced structural engineers on the planet, is actually where this story gets interesting. Because the engineers who called it impossible were not wrong to be skeptical. They were skeptical for exactly the right reasons. They just happened to be wrong about the outcome. To understand why this matters so much, and why the skepticism was both reasonable and ultimately incorrect, you have to go back to the beginning. You have to understand what concrete actually is, why it works, and why changing it is one of the hardest challenges in all of material science. Concrete is not a modern invention. The Romans were pouring it into harbors and vaults 2,000 years ago, and some of those structures are still standing today in better condition than bridges built 50 years ago. That longevity is not an accident. It is the result of a material that hits an almost impossible combination of properties all at once. It is cheap enough that even the poorest nations on Earth can afford to build with it at scale. It is strong enough to form the foundation of a 100-story skyscraper. It can be poured into literally any shape a human mind can design. It hardens without any special treatment. No kilns, no heat, no pressure required at the construction site. It does not rust the way steel does. It does not rot the way timber does. It does not shatter the way glass does. And once it is in the ground, it tends to stay there for a very long time, requiring very little maintenance compared to almost every alternative material. For the engineers who have spent entire careers designing with concrete, the material is not just a tool. It is a language. After generations of use across every climate, every soil condition, every type of structure imaginable, engineers understand exactly how concrete behaves. They know how it responds to stress. They know how it ages. They know its failure modes and its limits with the kind of intimate precision that only comes from building things out of a material for 100 years and watching what happens. The building codes that govern construction in every country on Earth are not abstract documents. They are the accumulated knowledge of every concrete structure that has ever been built, every one that has ever cracked, and every one that has ever failed. Changing the fundamental chemistry and behavior of concrete does not just mean developing a new material. It means convincing an entire global profession to rewrite everything they know. That is why the skepticism was not irrational. That is why engineers called it not possible. Not because they were being stubborn, because they understood the size of what was being proposed. And yet the problem on the other side of that equation is equally enormous and equally real. The carbon locked into cement production is not a rounding error that can be quietly managed at the edges. To make cement, you have to heat limestone to over 1400 degrees Celsius. At that temperature, the limestone breaks apart at a molecular level and releases carbon dioxide as a direct byproduct of the chemical reaction itself. This is the part that stops most people cold when they first understand it. Even if you powered every cement kiln on Earth with perfectly clean, perfectly renewable electricity, even if the entire energy source for the industry were completely decarbonized overnight, you would still release massive quantities of carbon dioxide into the atmosphere. Because the carbon is not coming from the fuel, it is coming from the rock. It is chemistry, not combustion. And you cannot capture your way out of chemistry with a cleaner power source. Now multiply that inescapable chemical reality by the scale at which the world consumes cement. China alone, between 2011 and 2013, used more cement than the United States consumed during the entire 20th century. Not in a generation, not across a decade, in 2 years. Entire cities were built from bare earth. Highways were pushed through mountain ranges that had never seen a road. Bridges crossed rivers that had never been bridged. This level of construction transformed a nation at a pace that had never been attempted before in human history, and it left behind a carbon footprint that will be measured and debated by climate scientists for decades. And China is not alone. India, Southeast Asia, Sub-Saharan Africa, every developing region on Earth is on a trajectory toward the kind of infrastructure build-out that China went through. The global demand for concrete is not declining, it is accelerating. This is the trap that the construction industry has been sitting inside for decades. A material so necessary, so embedded in the global economy, so deeply woven into the fabric of how we build everything, that nobody can afford to stop using it. But a material whose production process releases carbon at a scale that the planet genuinely cannot absorb without severe consequences. Researchers tried to chip away at this contradiction for years. Some experimented with replacing portions of the cement in concrete with industrial waste products like fly ash or blast furnace slag. Others developed geopolymer concretes that used entirely different chemical binding systems. A few focused on capturing the carbon at the cement plant before it reached the atmosphere. These efforts moved the needle somewhat. They were worth doing. But none of them resolved the fundamental economics of the problem at a global scale. The core process of making concrete, mix, pour, weight, stayed essentially unchanged for over a century. The question that the Chinese research team asked in 2025 was so simple that the most common reaction when engineers first heard it was not excitement, it was confusion. What if the problem was not what you put into the concrete, but what you do to it in the moments immediately after it comes out of the mixer? What if, instead of letting gravity and time slowly organize the particles inside fresh concrete, you applied mechanical force to compress and reorganize them yourself? Fresh concrete is not solid. Anyone who has ever watched a pour knows this. Right after mixing, it is a dense, heavy slurry, full of water, trapped air, and loosely arranged particles of cement paste and stone aggregate, all floating in a suspension. Normally, you guide that slurry into its mold, and then you wait. Gravity pulls some of the heavier particles downward. Vibration tools help the mix settle and release some of the larger trapped air pockets. And then, over hours and days, the chemical reaction called hydration slowly hardens everything into a rigid solid. This process has been the foundation of concrete construction for as long as modern construction has existed. The research team decided to interrupt it. Instead of pouring fresh concrete and waiting, they applied between 5 and 15 megapascals of mechanical pressure to the mix while it was still wet and workable. To put that in terms that make physical sense, that is roughly the kind of force you would find inside a heavy-duty industrial hydraulic press. The kind of equipment that bends steel beams and stamps car body panels. Applied to fresh concrete, the effect was immediate and dramatic. The particles were forced together so tightly and so quickly that the water and trapped air had nowhere to go but out. The concrete became denser, harder, and more uniform almost instantaneously. The researchers described it as the difference between a loosely packed bag of sand and a block of compressed stone. Same material, completely different internal structure. The technical measurement of this change is called porosity, which is the percentage of the material's total volume made up of tiny gaps, holes, and voids. In standard concrete, these microscopic voids are everywhere. You cannot see them without a powerful microscope, but they are there, and they matter enormously. Because those voids are where almost every long-term concrete problem begins. Cracks start at voids, because voids are stress concentrations where the material is locally weaker than its surroundings. Water infiltrates through voids, and with water comes the dissolved salts and chemicals that destroy concrete from the inside. In coastal environments and anywhere roads are salted in winter, those chemicals travel through the voids until they reach the steel reinforcement bars buried inside the concrete, where they trigger corrosion that can silently destroy a structure's structural integrity over decades before anyone sees a crack on the surface. When temperatures drop below freezing, water trapped inside voids expands as it turns to ice, and that expansion exerts enormous force on the surrounding material. Do that cycle thousands of times over the life of a bridge or a road deck, and the damage accumulates. In the compression cast concrete, the total porosity dropped by around 45% compared to standard concrete. Nearly half of the voids simply gone. But the most important thing that the researchers found was happening at a scale most engineers had never paid serious attention to. Inside any piece of standard concrete, at the microscopic boundary where the cement paste meets each individual piece of stone aggregate, there is a transition zone. This zone has been known in the research literature for decades. What has also been known, but not widely discussed outside specialist circles, is that this transition zone is actually the weakest part of the entire concrete structure. It is looser, more porous, and more vulnerable than either the paste or the stone on their own. When concrete fails under load, it almost always fails first at this boundary. Under the compression casting process, this transition zone tightened dramatically. The number of voids in this boundary region dropped by 35% compared to conventional concrete. The weakest link in the entire material chain got significantly stronger, without any change to the material itself. The lab numbers that came back from these tests were the first reason engineers started calling the results not possible. Compressive strength increased by over 80% in the highest pressure batches. Resistance to water intrusion improved substantially. Performance in freeze-thaw cycle testing improved. Resistance to chemical attack from chlorides and sulfates improved. And in the detail that made materials scientists put down their coffee and read the paper a second time, every single one of these improvements was achieved without adding a single new ingredient to the concrete mix. No expensive additives, no exotic supplementary materials, no reformulation of the basic recipe that the industry has been using for 100 years. The same sand, the same aggregate, the same cement, the same water, handled differently for approximately 10 to 15 minutes, produced a material that was fundamentally and measurably better by every standard metric the industry uses to evaluate structural concrete. What happened next was almost as unusual as the results themselves. The research team published everything, not a summary, not a carefully curated selection of their best results, everything. Raw data spreadsheets, microscopic imaging taken at extreme magnification, force and displacement readings from nanomechanical tests that allowed other researchers to verify the internal structural changes. All of it released under an open license, freely available for download by any engineer anywhere in the world. In an industry where proprietary methods are fiercely protected and licensing deals worth hundreds of millions of dollars are built on keeping process details secret, this level of transparency was almost shocking. And it was strategically brilliant, because when other engineers could check the work and replicate the findings in their own facilities, the objection that it was just good laboratory theater dissolved rapidly. That is when the not possible crowd started getting quieter, and a different kind of engineering conversation began. Running parallel to the compression casting research was a separate development that was solving a related but distinct problem, and the two technologies together are what turned global heads in 2025 and into 2026. Broad Group, a Chinese construction company with a reputation for doing things that most of the industry considers logistically implausible, had developed a structural panel system called B-Core. The panels look almost deceptively simple from a photograph. Two thin steel skins held apart by a precise internal lattice of hollow steel tubes arranged in a geometric grid. From a certain angle, They resemble the interior of an industrial waffle iron. But they are engineered to tolerances measured in fractions of a millimeter, and the logic behind them comes directly from aerospace engineering, specifically from the structural principles that allow an aircraft fuselage to be simultaneously very thin and extraordinarily strong. In a conventional aircraft fuselage, or a B-core panel, the secret is that stress is distributed through geometry rather than through mass. You do not make the structure stronger by adding more material. You make it stronger by arranging the material you have in a configuration that handles load more efficiently. The steel skins in a B-core panel handle tension and compression. The internal tube lattice handles bending and torsional forces. Together, the system produces a structural panel that weighs less than a tenth of a comparable reinforced concrete slab, while carrying similar structural loads under testing conditions. When Broad Group first announced those numbers, the not possible reaction from the construction world was almost immediate. A panel weighing less than a tenth of its concrete equivalent carrying the same loads? Engineers who had spent careers calculating concrete structural systems were deeply skeptical. Then the testing data started coming in, and the accelerated timelines became harder to argue with. A 10-story building in Chengdu was assembled using B-core modules in under 30 hours. Not as a stunt, not as a specially simplified demonstration structure, as a real building, with workers completing a floor of structure in hours, rather than the days or weeks a conventional concrete pour and cure cycle requires. The speed is not a product of workers cutting corners or rushing. It is a product of a system designed from the ground up for rapid assembly, the same logical principle that makes flat-pack furniture faster to assemble than custom carpentry. The components are designed to fit together, every connection point engineered to lock precisely. The seismic performance data was the element that converted the most skeptical structural engineers. Buildings in earthquake zones face a fundamental physics problem that concrete makes worse. Heavy structures hit by seismic energy have to absorb and redirect enormous forces because the mass of the building itself becomes part of the destructive equation. A lighter structure experiences less seismic force by the basic principles of physics, and B-core panels are dramatically lighter. Seismic testing showed the system handling shock and vibration with resilience that conventional concrete frames struggled to match. In the parts of the world where earthquake risk is highest, which includes some of the most densely populated regions on Earth, that is not a minor engineering footnote. It is a safety argument that speaks directly to the most serious concern any structural engineer has. What happens to the people inside when the ground moves? B-core and compression cast concrete are not competing technologies. They are solving different pieces of the same problem. Compression casting makes the concrete that does get used dramatically better. Stronger, denser, more durable, and produced with meaningfully less cement per unit of structural performance. B-core reduces how much concrete a building needs in the first place by replacing concrete slabs with a lighter, faster, and structurally competitive alternative. When you put these two directions together, the combined reduction in cement consumption, construction time, structural weight, and carbon emissions is significantly larger than either technology delivers working alone. That is the combination that caught serious attention from the global construction industry in 2025 and caused a wave of international activity that accelerated sharply into 2026. The speed of that international response was itself something that made old hands in the construction industry raise their eyebrows. Building codes in most countries update on timescales measured in years. Large construction companies move cautiously because structural failure is not an abstract risk. It is measured in human lives and careers. Patent filings from Germany, Japan, South Korea, and the United Kingdom, citing the original Chinese research, appeared within months. These are not academic references. They are companies and research consortiums committing legal and financial resources to the technology because they believe it is real and they do not want to be late. China exported 12.4 million metric tons of carbon-cured concrete additives to the United States, the United Kingdom, and Southeast Asia in 2026, a tenfold increase over 2 years prior. One of the world's largest cement producers signed a multi-year licensing deal to adapt B-core technology for European prefabricated construction. A German research consortium ran compression casting trials on a real highway project near Berlin. Japan's Obayashi Corporation launched a joint research program targeting meaningful cement reductions connected to the Osaka Expo build-out. South Korea's Hyundai Engineering announced plans to build a domestic B-Core panel factory as part of its smart city development pipeline. None of this activity is driven by environmental enthusiasm or corporate social responsibility language. It is driven by arithmetic. In markets where carbon is taxed or where emissions are capped and traded, a 40% reduction in cement use translates directly into lower regulatory costs. In any market anywhere, producing a stronger product using less of the most expensive ingredient in your formula is not a sustainability initiative. It is a competitive advantage. And a competitive advantage of this magnitude, in an industry that operates at this scale, is something no serious company can afford to observe from a distance while competitors move. The real-world validation data that preceded all of this corporate movement was essential in building the confidence that caused it to accelerate. On the Pingzhong River, 150 meters of bridge deck, built with compression cast concrete, were monitored continuously for 12 months, using embedded strain sensors and moisture monitoring systems. The in-place compressive strength averaged 61 megapascals, matching the laboratory predictions precisely. Zero visible cracking. Stable moisture readings throughout the entire monitoring period. Every data point from that year of observation is archived publicly and available for any engineer anywhere to download and independently verify. In Shanghai, prefabricated wall panels using B-Core adjacent construction methods in a pilot housing project showed a 15% improvement in thermal insulation performance and required substantially fewer post-installation repairs than conventional prefabricated panels. The engineers on that project were not motivated by environmental goals. They chose the material because it was stronger, cheaper, and came with comprehensive performance data. That combination, open science, real-world validation under actual service conditions, and a clear and demonstrable economic case, is what separates this moment from all the previous moments when someone claimed concrete was on the verge of changing. The difference this time is that the claim has receipts, and the engineers who were loudest in calling it not possible are now the ones asking how fast the new equipment can be delivered to their plants. The scale of what this could mean if adoption accelerates is genuinely difficult to frame without the numbers sounding exaggerated. Life cycle analysis models from multiple independent research groups suggest that switching just 30% of new structural concrete globally to the compression casting process could reduce annual carbon dioxide emissions by around 850 million tons. To give that figure context, that is more than the entire country of Germany produces in a year from every source combined: every power plant, every factory, every vehicle, every farm. One process change applied to less than a third of global concrete output, delivering a climate result at that scale. And that figure does not include the additional reductions that come from B-Core panels, reducing total concrete volumes in structures where they are adopted. If this changed how you think about the material you walk on and sleep inside every single night, hit like and subscribe. Turn on notifications so you never miss a video about the technologies that are quietly rewriting the world around us. And I want to hear from you in the comments. The engineers who called this not possible were smart, experienced professionals applying exactly the right level of scrutiny. If a change this significant can still surprise the people who know the most about it, what else is hiding right now in a material or a process so familiar that nobody is looking at it carefully enough?